So we are still waiting for some people to join, and then we'll be starting in another 2 minutes, maybe. So I think we can start now. And today we'll be looking into a little bit of X-ray photoelectron spectroscopy. And then we will also be discussing questions from the portions that we have covered, like IR, UV, and other spectroscopy methods, like fluorimetry and phosphorimetry. So we'll be looking into what questions have come in the previous years. Just 1 minute. Okay, so just start the presentation. So, X-ray photoelectron spectroscopy. Let us have an idea of what this is. So, we'll be talking about what background information is there, what is the instrumentation, and how does XPS work essentially. What are Auger electrons, and what are the instrumentations? How the spectrum looks like, and how to identify the peaks. Okay, so XPS is based on Einstein's idea about the photoelectric effect, which was developed around 1905. So the basic concepts is of the photons, which have ejection of the electrons from the surface when photons are impinged upon it. So whenever photons are hitting the surface, you're getting ejection of electrons. And gradually during the mid 1960s, Dr. Sigban and his group, they developed the XPS technique. And because of the XPS technique, they were awarded the Nobel Prize in Physics. So we know that X-rays, whenever they are hitting the sample surface, whenever the radiation is hitting the surface, the core electrons are getting activated, and they penetrate the sample to a depth on the order of a micrometer. And useful electron signal is obtained only from a depth of 10 to 100 Armstrong on the surface. So the sources of X-rays which can produce the photon with certain energies are MgK alpha photon with an energy of 1253.6 and an aluminium K alpha photon with an energy of 1486.6. So normally the sample is radiated with photons of a single energy, either magnesium K alpha or aluminium K alpha, and this is also known as monoenergetic X-ray beam because they are from a single energy source. So why are we targeting the core electrons? Now an electron near the Fermi level is far from the nucleus and they're moving all in different directions. So for in carrying out information about any particular atom, they will not be useful. Now Fermi level is the highest energy level. Okay, it is the highest energy level occupied by an electron in a neutral solid at absolute zero temperature. So the electron binding energy is calculated with respect to the Fermi level. Since the core electrons are close to the nucleus, they actually have the binding energies that are characteristic of that particular element. And also they have a higher probability that they will match the energies of the radiation that is being given, that is of aluminium K alpha and magnesium K alpha. Now, a little recap about binding energy. So, this is characteristic of the core electrons for each element. They are determined by the attraction of the electrons to the nucleus. If an electron with energy X is pulled away from the nucleus, attraction between the electron and the nucleus decreases and the binding energy decreases. So, there will be a point when the electron will be free of the nucleus. Now, as you can see in the diagram, suppose this is the point with zero energy of attraction between electron and nucleus. So at this point, electron is free from the atom. And then you have some electrons which are attracted to the proton with certain binding energy X. So if we have energy levels like this, where we have a vacuum level, from the lowest state of energy, the highest level that can be there is the vacuum level, and then there is the Fermi level. So at absolute zero, the electrons are filling up from the lowest energy states, and when the electrons are occupying up to this particular level, that is a Fermi level, the neutral solid is in the ground state. Okay, and after that, whatever is the energy jump, that will be the work function. Okay, that will be the work function. So let us explain it in a proper manner. So here is how the ejection of core electrons is taking place. As you can see, H nu radiation is going and then it is getting ejected. So the characteristic binding energies of the electrons are actually keeping them in their orbitals. And what are influencing the binding energies? At the atom type is influencing the characteristic of the adjacent atoms, orbital kinds, everything is influencing the binding energy. And the binding energy which are of the electrons which are being emitted from the sample surface, they are measured by the XPS. So we all know that the mechanism of photoionization is utilized to eject the electrons from the surfaces. And we know that aluminium K alpha radiation is being used, or magnesium K alpha is used, and the photon is penetrating to a depth of approximately 1 micrometer. So when a photon is interacting with the sample atom, the photon's energies, it is ionizing the core electrons and they are ejected from the atoms. And within the bulk of the sample, mean free path of the ejected electrons is very small due to interaction with the surrounding atoms. Okay, it is very small due to interaction with the surrounding atoms. But the electrons which are expelled from atoms in the sample's top 5 nanometer layer, they have a high chance of leaving without further interaction. Now, these electrons will pass into the ultra high vacuum UHV conditions within the spectrometer to ensure that the electrons are not scattered by gas molecules and to limit surface contamination during the analysis. So, if we are using an spectrophotometer, which is actually the electron energy analyzer in this case, they will measure the kinetic energy of the ejected electrons. And the original binding energy, which is experienced by the electron in the sample, they can be calculated from the EK with this simple relationship. So, EK is equal to h nu minus EB minus phi. So, here EK is the kinetic energy of the ejected electron. EB is the binding energy of the electron, H nu is the incident photon energy, and phi is the work function of spectrophotometer. Now, the different atoms have different electron shells with different binding energies. Each element has unique binding energy, that is EB, and this can be used to identify the elemental composition of the sample surface. The number of emitted photoelectrons with various EK is now counted, and then an XPS spectrum is generated, which can facilitate the identification of all elements in all states except for hydrogen and helium. So please note down the relationship EK is equal to h nu minus EB minus phi. So where EK is the kinetic energy of the ejected electron, h nu is the incident photon energy, phi is the work function of the spectrometer, and EB is the binding energy of the electron. So this is how the XPS instrument looks like. So this is located at University of Texas. So this is quite the instrument. And you can also note down that XPS is also known as ESCA. Okay, it is also known as ESCA, that is electron spectroscopy for chemical analysis. Okay, ESCA is also known as electron spectroscopy for chemical analysis. And this technique is widely used because it is very simple to use and the data is easily analyzed. The data analysis is fairly easy. Now this is being controlled by a computer system, and the computer will dictate by whatever codes you are giving. They will control the X-ray type and they will prepare the instrument for analysis. So what kind of angles will be there, how the sample will be irradiated, when the sample will be irradiated, everything is controlled by a set of conditions. You have to just set the conditions and the computer will do its job. The instrument also uses different pump systems to reach the goal of an ultra high vacuum environment. And why we are using the UHV environment? Because we want to prevent the contamination of the surface and we want to have an accurate analysis. Okay, so this is how the pump systems work. So if we were to label, then first we need an X-ray source. Then there is an ion source. There's a elemental analyzer and a sample introduction chamber. So what happens is the sample will be first introduced through a chamber that is contact with the outside environment. It will be closed and pumped to low vacuum. After the first chamber is at the low vacuum stage, the sample is introduced into the second chamber in which a UHV environment exists. So this is the first chamber and this is the second chamber that is in UHV conditions. This is the schematic of the XPS system. So we can have in the top three, you have three colorful schematics, one for the X-ray, one for the ion, and one for the SIMS analyzer. And then we have a sample introduction chamber. You have a sample holder, and then you have the electron gun, the detector. You have two slits as well. And then we have pumps. It's not changing. Okay, so how does the technology work? As we have already talked about, let us talk about the bullet points again. So the X-ray beam is emitting photoelectrons, and X-ray energies can be of two energies, aluminum K alpha and magnesium K alpha, and they are penetrating up to a micrometer. And the XPS spectrum only contains about the top 10 to 100 angstrom of the sample. We are using a UHV to eliminate excessive surface contamination. The CMA that we saw here, okay, this is the CMA, okay, this particular portion, that is actually the cylindrical mirror analyzer. and it measures the kinetic energy of the emitted electrons. Finally, whatever spectrum we are getting, it is plotted by the computer from the analyzer signal, and the binding energies, they are determined from the peak positions and the elements present in the sample identified. Now, why does XPS need UHV? Okay, why are we using again the ultra high vacuum conditions? We already have talked about this. First, that the contamination of the surface can be avoided as it is surface sensitive technique. Since we are telling only the top 10 to 100 Armstrong of the sample is being considered for the spectra. So if you are contaminating the surface, then it will produce a incorrect XPS signal. So we will not be able to analyze the surface of the composition accurately. So we are preventing the contamination of the surface by using UHV. And the pressure of the vacuum system is also less than 10 to the power minus 9 torr. So how are we removing the contamination? Suppose there is some kind of contamination. How are we going to remove the contamination? So what we can do is we can either use heat and oxygen that can remove the excess hydrocarbons that are acting as impurity, or we can also bombard the sample with argon ions. Okay, we can bombard the sample with argon ions, and although the XPS technique could cause damage to the surface, but it won't be that but it won't be that conspicuous. It will be actually negligible. So this is also a schematic diagram of how the X-rays are penetrating through the atom to the core electrons, and then the core electrons are getting ejected. So you can also draw this diagram when asked how the XPS principle works. This is another kind of diagram which you can draw to show only the topmost layers are getting ejected, and the X-rays are first penetrating down to the core electrons, and the outermost layers are getting affected. Now, what kind of ejections can be there? Now, the X-rays can penetrate to the core electrons of the atoms in the sample. Now, some electrons will be released without any problem, and they will give the kinetic energies that are characteristic of their elements. But other electrons will come from inner layers and they will collide with other electrons of the upper layers. So, this is what is happening. So, X-rays are coming down to the core electrons. Some of them get ejected without any problem, but here the topmost layer is also there and the innermost layer is also there. So while coming up, they can collide with the electrons. The paths can coincide. So, so when these things are happening, the electrons will be lower energy. Okay, they will be of lower energy and they will not give the characteristic kinetic energy that is expected. So these kind of collisions will contribute to the noise signal of the spectrum. Okay, these will contribute to the noise signal of the spectrum. So this is another representation of what is happening. So the noise, so the pink parts, they are the electron without collision, and the reds, they are the with collision. So the noise signal is coming from the electrons that collide with other electrons of different layers. And the collisions, they are causing a decrease in energy of the electron. So it will no longer contribute to the characteristic energy of the element here. So just 1 minute. I think someone has messaged. Just 1 minute. Yash, if you want to say something, you can say in the chat box. Slide is not scrolling. So which slide is not scrolling? So from which slide have you not seen?
Ma'am. Hello.
So from the introduction to now, no slide you have seen.
यस मैम, स्टार्टिंग से वही पहला स्लाइड ही दिखाई दे रहा है और दिखाई नहीं दे रहा है कुछ भी।
अरे तो फिर तो बताना चाहिए ना। आई एम सेइंग दैट यू कैन सी
मैम
दिस,
हम
यू
तो
कैन सी दिस, तो
हाँ मैं हम तो सर क्वेश्चन जो हैंड रेज किया और मैसेज ही कर रहे हैं जो।
तो यू शुड स्टार्ट स्पीकिंग ना कि नहीं दिख रहा है करके। इतना सारा आई हैव कवर्ड ऑलमोस्ट 21 स्लाइड्स, हम लोग कुछ नहीं बोले, कोई एक भी नहीं बोला। अभी
मैम
तुम
हम
लोग
तो सर
एक
नेटवर्क प्रॉब्लम है इसलिए बार बार आउट जाके इन हो रहे, आउट जाके इन हो रहे, फिर भी सेम प्रॉब्लम दिखाई दिया। हम सर नेटवर्क प्रॉब्लम की वजह से ऐसा हो रहा है।
तो बाकी लोग भी तो बोल सकते हैं कि स्लाइड्स नहीं दिख रहा है करके। ठीक है,
हाँ,
एनीवे।
बाकी लोग मैम बार बार इन आउट इसीलिए शायद हो रहे होंगे मुझे लग रहा है। ओके मैम।
ठीक है, फाइन, आई विल बी गिविंग यू द स्लाइड, बट देखते हैं बाकी अभी। और एक लास्ट पार्ट का थोड़ा बस मैं रिपीट। सो आई वाज, अभी दिख रहा है एटॉम एंड द एक्सरे।
यस मैम दिखाई दे
अभी
रहा है आटम,
एटॉम एंड द
आटम
एक्सरे
एंड
दिख रहा
एक्सरे।
है। अच्छा ठीक है, सो विल
यस मैम।
मूव ऑन। यहीं से हम लोग एटम एंड द एक्सरे वाला देखेंगे। So the rest of you also pay attention ना, you should inform me if something is going wrong. एक ही स्लाइड को जब टाइटल स्लाइड करके रखा है एंड आई एम एक्सप्लेनिंग कंटिन्यूअसली एंड आई एम सीइंग दैट यू कैन सी इन दिस डायग्राम दैट डायग्राम, तो फिर आप लोग को तो पता ना चाहिए कि क्या हो रहा है। आर यू नॉट लिसनिंग और आर यू नॉट पेइंग अटेंशन, क्या हो रहा है? नेवर माइंड। सो these are the x-rays on the surface, ठीक है? And as they are penetrating to the core electrons, they are getting emitted, but they are also colliding with the upper layers, and when they are colliding with the upper layers there is noise. Okay, so some electrons will be released without any problem, which will give the kinetic energies that is characteristic of their elements, and other electrons will come from the inner layers and collide with the other electrons of the upper layers. So these are the X-rays and the electrons. A representative diagram is what happening. So the noise signal that comes from the electrons that collide with other electrons of different layers, these collisions will cause a decrease in energy of the electron, and it will no longer contribute to the characteristic energy of the element. So what kind of electrons can the cylindrical mirror analyzer detect? Now going back, since you have not seen the diagram at all, so this is how the instrument looks like. Okay, this is also known as ESCA, and this is controlled by a computer system. It has different kinds of pump systems. Okay, so this is the X-ray source, this is the ion source, this is the SIMS analyzer and the sample introduction chamber. And this is how the side view of the XPS system looks like. Okay, this is how the XPS system looks like. So we are talking about the CMA part. Okay, we are talking about the CMA part. CMA in the sense cylindrical mirror analyzer. So what kind of electrons can this mirror analyzer detect? So it not only can detect electrons from the irradiation of X-rays, it can also detect electrons from irradiation by the electron gun. Now the electron gun is located inside the CMA while the X-ray source is located on top of the instrument. And the only electrons which are normally used in a spectrum from irradiation by the electron gun, they are known as the Auger electrons. Okay, they are known as the Auger electrons, and they are also produced by the X-ray irradiation. So when the core electrons leaves a vacancy, the electron of higher energy will move down to occupy the vacancy while releasing energy by first photons and the other is Auger electrons. So each Auger electron carries a characteristic energy which can be measured. And what are the ways to produce these kind of Auger electrons? So first the X-ray source will irradiate and they will remove the electron from the core level. The core electron will get removed and another electron from a higher position will occupy the vacancy and the core electron will leave the atom. Now the energy released will be given to a third higher level electron, and this is the Auger electron which can leave the atom now. Now the axial electron gun, they can irradiate and remove the core electron by collision, and once the core vacancy is created, the Auger electron process occurs in the on this kind of way. So let us think about the Auger electron here. So electron gun is hitting the core electron, and after it is going away as a free electron, then the electron vacancy is there. So now electron of a higher energy will occupy the vacancy of the core level, okay, and the electron that is released, that will be analyzed here. Okay, so 1, 2, 3 and 4 are the order of the steps in which the electrons will move in the atom when hit by the electron gun. So another schematic of what is going to happen in the Auger electron spectroscopy, that is AES. So there are two kinds of AES, atomic emission spectroscopy and Auger electron spectroscopy. So be careful about the question that is being asked. Now cylindrical mirror analyzer, what is the role of that? Now the electrons that are ejected, they will pass through a device called a CMA, and it has two concentric metal cylinders at different voltages. Now one of the metal cylinders has a positive voltage and the other has a zero voltage. So this creates an electric field between the two cylinders. Okay, this creates an electric field between the two cylinders. And the voltages on the CMA for XPS and the Auger electrons, they are different. Okay, voltages on the CMA for XPS and Auger electrons, they are different. When the electrons are passing through the metal cylinders, they just collide with one of the cylinders, or they can just pass through. Now, if it is a very high velocity electron, then it will collide with the outer cylinder. If it is going too slow, then it will collide with the inner cylinder. And only the electrons which has the right velocity, they will go through the cylinders to reach the detector. And with a change in the cylinder voltage, the acceptable kinetic energy will change. And then you can count how many electrons have the correct kinetic energy to reach the detector. So cylindrical mirror analyzer looks like this. We have given the complete schematic diagram, but the cylindrical mirror analyzer, if you zoom into it, it will look something like this. Okay, so the X-ray sources are there. So various kinds of directions the electrons are passing through. So some will hit the outer cylinder if they are passing in a very high velocity. Some will hit the inner cylinders like this, and only a few will be having the correct energy. Okay, only a few will be having the correct energy, and those will be detected. So we have already gone through this equation where we were writing EK is equal to h nu minus 5 minus EB, and here we are writing K, kinetic energy is equal to h nu minus binding energy minus work function. Okay, it is the work function. Now h nu, what it is? It is the photon energy from the X-ray source. Okay, it is a photon energy from the X-ray source. Now if we were plotting a graph between the electrons and the binding energy, then we can see a characteristic graph like this, and the kinetic energy can be plotted depending on the binding energy. Now each peak here, it represents the amount of electrons at a certain energy, which is a characteristic of some element. Okay, it is a characteristic of such element. Now, how will we interpret the XPS system? Okay, how will we interpret the XPS system? For this, the first thing that we have to see is the background noise. Okay, we have to take the background noise first. Now, we have to know that the X-ray first, it hits the electrons in the bulk, that is the inner electrons. And whenever these electrons are colliding with the other electrons, they are decreasing the energy and they're contributing to the noise. So, they will have lower kinetic energy than the peaks. And if they have lower kinetic energy than the peaks, then the background noise is also increasing with the binding energy, because the sum of all noise is taken from the beginning of the analysis. Okay, the sum of all noise is taken from the beginning of the analysis. So the features of an XPS spectrum is that first, the XPS peaks are sharp. In an XPS graph, it is possible to see Auger
Madam,
electron
hello.
peaks.
Hello, madam. Can you repeat the
Hello,
previous slide? Hello, madam.
the previous.
Can you kindly
Yes,
repeat the previous slide, madam?
this one.
Yes, ma'am.
So here, okay, we had explained this concept over here. Just wait. Okay, here we were explaining that we are getting a noise signal when the electrons are colliding with other electrons of different layers, because the X-rays are first hitting the inner layers. Okay, X-rays are first hitting the inner layers, and when these electrons are getting emitted, they are hitting the electrons from other layers. So a noise is coming up. So that is what they're saying about the background. that the peaks will have the correct energies, but some electrons which are present in the inner levels, when they are colliding with the other electron of different layers, they will not contribute to the characteristic energy of the element. So what it is, it will contribute to the background or the noise. Okay, it will contribute to the background or the noise. So first we have to take consideration of the background noise. Then XPS peaks, they're just saying the features of the XPS spectrum. So if you are seeing very broad peaks, then those are the Auger peaks. If you are seeing the sharp peaks, then those are the XPS peaks. So this is how an XPS spectrum looks like, because this is a broad peak, this is a Auger peak. Okay, this is an Auger peak, and this is the number of electrons versus binding energy, and then you're getting an O1s, okay, and a O2s. So the sharp peaks are actually characteristic of the element. Okay, sharp peaks are characteristic of the element. So we have oxygen, carbon, and aluminium peaks as of now in this spectra. If we are again zooming onto the Auger spectrum, okay, if we are zooming onto the Auger spectrum, we see that the graph in an Auger spectrum, it grows up as the kinetic energy increases. Okay, it goes up as the kinetic energy increases. Now, how do we find out what XPS peaks are for which element? So, plot will have characteristic peaks for each element that is found in the surface of the sample, and we already have pre-assigned tables with kinetic energy and binding energy which are assigned to each element. So each element has a characteristic kinetic energy and binding energy, and once we get the plot, seeing the position of the binding energy and looking at the kinetic energy, we can find out which element has been assigned and at what position it is there. So you can look for the designated value of the peak energy from the graph, and you can find the element that is present on the surface. So how do we distinguish between an electron gun beam and a X-rays? So X-rays, what they do, they hit all the sample areas simultaneously, and this will permit data acquisition that will give you an idea of the average composition of the whole surface. Similarly, an electron beam from a gun, it can be focused on a particular area of the sample to determine the composition of selected areas of the sample surface. And why is XPS technology preferred? Because it is considered as non-destructive. Whatever little damage to the surface is done, it is not conspicuous at all. And also it produces soft X-rays to induce photoelectron emission from the sample surface. So we are getting lots of informations about surface layers or thin film structures. Okay, so we are getting lots of information about surface layers or thin film structures. So what kinds of applications does it have? So it has great applications in polymer surfaces for studying the surfaces of the polymers, in catalysts, in corrosion and adhesion, because the surface properties can tell a lot about what kind of surface it is and what can be done to protect such surfaces or enhance the properties of the surfaces. So in dielectric materials, in semiconductors, in electronics packaging, magnetic media, and thin film coatings also, XPS technology is used. So for XPS, we can study some different kinds of spectra also, but not in too detail, because just the instrumentation is used. Okay, mainly it is used in elemental analysis. Okay, for quantitative analysis also. How we are going to do the quantitative analysis? Quantitative analysis requires the measurement of the relative peak intensities and the intensity of the peak, which will depend on the atomic concentration of the element present in the surface film. Okay, and for chemical state analysis also we can use that. We can find out the chemical bonding nature also, nature of functional groups also, and we can also see the oxidation states of the atoms. An important capability of the XPS is its ability to distinguish the same element in different chemical states, because of the binding energy. Okay, because of the binding energy, of the electron, which is different because of changes in the charge density around that element by oxidation. Also, if we are studying thin surface films or films, then it is called in-depth surface analysis. Okay, in-depth surface analysis, in-depth distribution of the elements in the film. So this can be done, like XPS can be used to find out how the surface of the thin film looks like, how the distribution of elements is there, and whether the distribution of the elements is homogeneous or not. Okay, and XPS is applicable to a wide variety of materials, from biological materials to metals. So you can use this extensively. Mostly solid samples are analyzed by XPS. Okay, solid, gaseous, liquid mainly can be analyzed, but the good results are obtained with solid samples, and the quantification is quite good. Now, if we were to list the limitations of X-ray photoelectron spectroscopy, then one thing is that it is enabled to detect hydrogen and helium. Okay, it cannot detect hydrogen and helium. Apart from that, many elements can be detected by XPS. Next, it is not suitable for trace analysis. Okay, it is not suitable for trace analysis. Another is that the sensitivity is not too much. It is only moderate sensitivity. Okay, it has only moderate sensitivity, and mainly poor spatial resolution is there. Okay, mainly poor spatial resolution is there. So how can we obtain a good signal output from a XPS instrument? We can just tune the sensitivity by using better sources. Okay, we can just use the better sources to tune the sensitivity. Also, UHV we have already talked about, that the samples must be compatible with the ultra high vacuum environment. So here we can also reduce the time per experiment if we are using a monochromator. Okay, because the XPS spectra, they take a long time to obtain. So the use of a monochromator, they can reduce the time per experiment. So another some kinds of examples of systems which can be studied by XPS are, I'm talking of surface reactions. So you can analyze some kind of stains or residues on surfaces and study the elemental analysis of those residues. You can also have reactive frictional wear of solid-solid reactions. Then you can do an depth profiling. Okay, it is called a depth profiling, where you are using something known as a sputter source. Okay, it is called a sputter source. So this removes successive layers from the surface of a sample, and it allows for the quantification of element depth profiles. And this is useful in the composition of thin films. We are also
मैम
using XPS nowadays for imaging of, yes.
मैम स्लाइड नहीं दिखाई दे रहा है अभी.
हाँ, मैं स्लाइड से बता भी नहीं रही हूँ. I'm just talking like that.
Okay.
So there is no slide here. Okay, I'm just talking. Okay, so we can also use XPS for imaging of surfaces, and we can also use them for angle dependence measurements. So whenever we are changing the angle of measurement, the depth of the information which can be gathered, we can vary that by 1 to 10 nanometers. And here why we are doing angle dependence measurements, it is used to determine the concentration of additives in the surface region. Okay, this can be used to determine the concentration of additives in the surface region. So we can calculate the elemental composition, we can calculate the empirical formula determination, we can find out the chemical state, the electronic state, we can find out the binding energy, and also the layer thickness we can find out. Now there is also something known as a UPS. Okay, there is also something known as the UPS, or ultraviolet photoelectron spectroscopy. Okay, ultraviolet photoelectron spectroscopy. So what is ultraviolet spectroscopy? Here essentially पहले ऐसा होता था that there used to be a gas or vapor, and that was irradiated with a narrow beam of UV radiation. So now better instruments have come up, and the photoelectrons that are produced, they are usually passed through a slit into a vacuum region, and then they are deflected by the magnetic or electrostatic fields to give a energy spectrum. And this is very sensitive to the near surface region. So I'm going to show you the diagram, a schematic diagram for this thing. Just wait. So as you can see, this is the schematic of a basic UPS instrument. And at the start of the module, you can have a sample collection source. And in this instrument, there is no optics. Okay, there is no electron multiplier. So we have separate chambers for the sample and the analyzer. And both of them are in the ultra high vacuum conditions. So two main areas which the UPS is used to study is the electronic structure of solids and the adsorbed molecules and metals. So this is like absorption behavior of the materials. And the specific examples of UPS studies, they include first the measurement of molecular orbitals energies, which can be compared to theoretical values that can be calculated from quantum chemistry. Also, we can determine and assign the bonding, non-bonding and anti-bonding molecular orbitals. Okay, we can determine and assign the bonding, non-bonding and anti-bonding molecular orbitals. You can also find the binding and orientation of adsorbed species on the surface of solids. You can also find the band structure mapping in K-space with angle resolved techniques. Okay, you can see the band structure mapping in K-space with angle resolved techniques. So this is also a kind of photoelectron spectroscopy. So here we have covered X-ray photoelectron spectroscopy and ultraviolet photoelectron spectroscopy. And the difference is that whereas the UPS, it focuses on ionization of valence electrons, XPS is able to go one step further and it ionizes the core electrons and it pries them away. And here the main goal in either of the spectroscopy is that we are gaining information about the composition, electronic state, chemical state, binding energy, and more importantly, the surface region of the solids. So a lot of qualitative and quantitative information can be learnt about the surface of the solids. And basically, there is a few basics that are always common to all the instrumental setups of the photoelectron spectroscopy. First, एक तो radiation source होना चाहिए, okay, and they must be fixed energy radiation sources, क्योंकि we are not going, because the electrons have to match, okay, the energies of the radiation sources, they must match with that of the core electrons, so they cannot just vary. And how are the sources varying? So the XPS sources come from the X-rays. हम लोग already discuss कर चुके थे, मैग्नीशियम का K alpha and एल्यूमिनियम का K alpha X-ray यूज किया जाता है XPS में. UPS का होता है गैस डिस्चार्ज लैंप से, ओके, UPS का होता है गैस डिस्चार्ज लैंप से. And we are now going for analyzers. Okay, so now photoelectron spectroscopy analyzers, they have various types of electron energy analyzers. Okay, we have various types of electron energy analyzers. Now a high vacuum environment is required for both kinds of spectroscopy. जहां पे XPS में एक ही चैम्बर था, UPS में हम लोग देख रहे हैं कि it is a must. ठीक है, पूरा एक्सपेरिमेंट ही हाई वैक्यूम में क्रिएट किया जा रहा है. So it keeps the surface of the sample clean and also keeps the rest of the environment free from interferences like gas molecules. So suppose we are studying a surface और उसमें कुछ gas molecules आ गए, so the high vacuum is used to keep that surface free of contamination. So many kinds of radiation sources we can use. The gas discharge lamp जो हमने UPS के लिए बोला है, we can use a helium discharge lamp. Okay, we can have a helium discharge lamp. And XPS का monochromatic beam use करना चाहिए. So we can use synchrotron radiation sources. Okay, we can use synchrotron radiation sources. Now this is useful in studying valence levels, as it provides continuous polarized radiation with high energies of greater than 350 electron volts. But when we're choosing a radiation source, we have to see the kinetic energy that is involved. So what the source is setting the kinetic energy of the photoelectrons, we need to see that आयोनाइजेशन होने के लिए एनर्जी ज्यादा होना चाहिए, ऑल्सो एक एनालाइजर भी होना चाहिए विच कैन मेजर द काइनेटिक एनर्जी ऑफ द रिलीज फोटो इलेक्ट्रॉन्स. सो हम लोग एक्सपीएस में देखे हैं कि इलेक्ट्रॉन गन्स वर यूज्ड इन कंजंक्शन विद एक्सरेज टू इजेक्ट फोटो इलेक्ट्रॉन्स. ओके, बट इलेक्ट्रॉन गन के भी कुछ एडवांटेजेस एंड डिसएडवांटेजेस होते हैं, जैसे कि इलेक्ट्रॉन गन में हम लोग इजीली फोकस कर पा रहे हैं इलेक्ट्रॉन बीम को, और फोटो इलेक्ट्रॉन्स को कॉन्स्टेंटली वेरी कर सकते हैं एक्साइटेशन में. बट इलेक्ट्रॉन गन की वजह से भी, बिकॉज देर इज सम स्कैटरिंग ऑफ द इलेक्ट्रॉन्स ऑल्सो, बैकग्राउंड रेडिएशन भी ज्यादा हो जाती है. ओके, बैकग्राउंड रेडिएशन भी ज्यादा हो जाती है. So what else? The analyzers that we have discussed, analyzer we can use kinetic energy analyzer use कर सकते हैं और electrostatic analyzer भी use कर सकते हैं. So kinetic energy analyzer में होता है कि if we are having higher energy of photoelectron, स्पेक्ट्रा का रेजोल्यूशन कम हो जाएगा. ओके, सो काइनेटिक एनर्जी एनालाइजर में क्या होता है ना, इफ यू आर हैविंग हायर काइनेटिक एनर्जी ऑफ द फोटो इलेक्ट्रॉन्स, देयर इज अ चांस दैट द स्पेक्ट्रा माइट बी लोअर इन रेजोल्यूशन. बट डिफ्लेक्शन एनालाइजर्स में होता है दैट यू कैन ऑल्सो सेपरेट आउट द फोटो इलेक्ट्रॉन्स थ्रू एन इलेक्ट्रिक फील्ड by forcing the electrons to follow different paths according to their velocities. We have already seen that in a CMA kind of a setup where they are separating out the photoelectrons by forcing the electrons to follow different paths according to their velocities, giving a better resolving power. So deflection analyzers are always better than kinetic energy analyzers. So different kinds of analyzers we have seen, like a CMA we have seen, like a cylindrical mirror analyzer. दूसरा काइंड ऑफ एनालाइजर्स भी होते हैं, जैसे कि प्लेन मिरर एनालाइजर होता है, पीएमए. ठीक है, पीएमए इज बेटर, सॉरी, सीएमए इज ऑलवेज बेटर देन पीएमए. ओके, बिकॉज दे हैव अ they can overcome the low transmission kind of problems, and they also have higher sensitivity and resolution is always better. दो सिलेंडर्स होते हैं जहां पे हम लोग एक पोटेंशियल डिफरेंस मेंटेन कर रहे हैं. सो वी हैव टॉक्ड अबाउट द सीएमएस. ऑल्सो दूसरा भी होता है, एक प्लेन मिरर हो सकता है, सिलेंड्रिकल मिरर हो सकता है, और एक काइंड ऑफ होता है डिफ्लेक्शन एनालाइजर जो हम लोग बात किए. डिफ्लेक्शन एनालाइजर में हो सकता है सिलेंड्रिकल डिफ्लेक्शन एनालाइजर और एक स्फेरिकल डिफ्लेक्शन एनालाइजर. इन एनालाइजर्स के रेजोल्यूशन ठीक ठाक होते हैं, बट उनका ट्रांसमिशन का थोड़ा प्रॉब्लम होता है. ओके, उनके ट्रांसमिशन का थोड़ा प्रॉब्लम होता है. एंड जैसे हम लोग सीएमए में देखे एक कि दो सिलेंड्रिकल ऐसा था, एसडीए में जो स्फेरिकल डिफ्लेक्शन एनालाइजर है, दो कंसेंट्रिक हेमिस्फीयर्स रख देते हैं. ठीक है, दो कंसेंट्रिक हेमिस्फीयर्स रख देते हैं. सो यहाँ पर भी वही वाला इफेक्ट आ जाता है दैट ओनली द फोटो इलेक्ट्रॉन्स ऑफ द करेक्ट एनर्जी दे आर एबल टू पास थ्रू द डिटेक्टर with the right arc, and they are exiting instead of colliding with the side walls of the hemispheres and becoming lost. Okay, they are not becoming lost. So SDA, इधर अगर हम लोग डिफ्लेक्शन वाला यूज कर रहे हैं एनालाइजर, तो वी कैन यूज द spherical deflection analyzer, and if you are using a mirror analyzer, then we can use the cylindrical mirror analyzer or the CMA. So this is mostly about your X-ray photoelectron spectroscopy and your UPS. So mainly instrumentation वगैरह ही आता है. So let us take now a break of 10 minutes and let us come back. We will discuss the questions arising from UV, IR, fluorimetry, phosphorimetry and XPS today. So if there are some problems also, I will ask you like I will tell you how to approach these kind of problems, and structure determination के लिए भी हम लोग कैसे approach करेंगे, that also I will tell you. So take a 10-minute break and we will come back. So while we're taking the break also, I'm giving you the links of several presentations and practice problem sets. Please go through them and download and keep in a folder. Okay, so let us continue with our question answer session. Okay, we are going to continue the question answer session. So first, right, we are going to do the questions for IR, UV, and XPS, fluorometry, and phosphorimetry. Okay, we're going to see what questions have come. So first, you write what are the advantages of FTIR instruments? What are the advantages of FTIR instruments? Okay. Next, right? What is meant by photo emission? What is meant by photo emission? What is meant by photo emission? Explain how it can depend on structure of molecule. Explain how it can depend on structure of molecule. Next, right? The acetylene molecule has a characteristic absorption. The acetylene molecule has a characteristic absorption at 2200 centimeter inverse in the IR spectra. In the acetylene molecule has a characteristic absorption at 2200 centimeter inverse in the IR spectrum. Calculate the energy and frequency of the IR radiation absorbed by acetylene. Calculate the energy and frequency of the IR radiation absorbed by acetylene. Next you write, in what way does fluorescence spectrometry have distinct advantage over UV visible spectrophotometry? In what way does fluorescence spectrometry has distinct advantage over UV visible spectrophotometry? Next, why is water not used as a solvent in IR spectrometry? Why is water not used as a solvent in IR spectrometry? State Lambert's law, and derive relationship, between the absorbance and the thickness of the absorbing medium. State Lambert's law and give the relationship between the absorbance and thickness of the absorbing medium. Next. Again, the advantages of FTIR instruments had come in another year, it is 2012. Give a tick mark there. Yes. Next is describe the quantitative applications of IR spectrometry. Describe the quantitative applications of IR spectrometry. Describe the quantitative applications of IR spectrometry. Next, right? Explain the factors on which fluorescence and phosphorescence depend. Explain the factors on which fluorescence and phosphorescence depend. Now here is a problem for you. You write that one for UV. A compound of formula weight 280, a compound of formula weight 280 absorbed 65% of the radiation, absorbed 65% of the radiation at a certain wavelength, in a 2 centimeter cell, in a 2 centimeter cell at a concentration of at a concentration of 15 milligram per centimeter inverse, sorry, centimeter cube, at a concentration of 15 milligram per centimeter cube. Calculate the molar absorptivity, calculate the molar absorptivity of the compound at this wavelength. Calculate the molar absorptivity of the compound at this wavelength. Next, write state Beer-Lambert's law, state Beer-Lambert's law, and list the deviations observed from the law. State Beer-Lambert's law and discuss the or list the deviations observed from this law. Then in many papers, the spectrophotometric, like instrumentation of fluorimetry and phosphorimetry have been asked. So you just write in notes instrumentation of fluorimetry and phosphorimetry. Next, a very specific question. If you have not learned about fluorescence and phosphorescence, you cannot answer this question. For 4 marks, it had come. Differentiate between internal conversion and inter-system crossing. Differentiate between internal conversion and inter-system crossing. For this question, it is not just sufficient to write the definition. You will have to draw the Jablonski diagram. You will have to show what it means for internal conversion and inter-system crossing, and you will also say what happens as a consequence of that. So for internal conversion, we can talk about fluorescence. For inter-system crossing, we can show that it is forbidden, and that is why phosphorescence occurs. And the phosphorescence occurs at a delay or a time lag because of the inter-system crossing. Okay. So you have to draw the diagram and then explain. Now, one question had also come about discussion of chemiluminescence. Okay. Discussion of chemiluminescence. That also had come. Next, you write, this is an important question. Enlist different types of species. Enlist different types of species that may absorb. Enlist different types of species that may absorb in the UV visible region of the spectrum. In the UV visible region of the spectrum. Enlist different types of species that may absorb in the UV visible region of the spectrum. Explain the nature of transitions. Explain the nature of transitions involved in any one of them. Explain the nature of transitions involved in any one of them. So here what you will do, you can give the different kinds of compounds that are absorbing. You can give ketones, aldehydes, alcohols, okay. Different types of species you can give. You can also give alkenes, alkynes, okay. All of this you can give, and then you can explain the nature of transitions. Transitions in the sense that what we had discussed in the very first class about sigma to sigma star, pi to pi star, n to pi star, okay, n to sigma star. And then if you pick a good molecule where it will have several types of transitions, it will be better because you can show this kind of transitions and you can explain why these transitions are occurring. For example, if you pick a group with a double bond as well as a non-bonded lone pair of electrons, then you can talk about n to pi star, n to sigma star, pi to pi star, all of these transitions you can write about. Next, write state necessary conditions. State necessary conditions. State necessary conditions for a molecule to show. For a molecule to show. First point, UV absorption. Second point, IR spectrum. State necessary conditions for a molecule to show, first point, UV absorption, and second, IR spectrum. Now you'll be able to write this very easily. Okay. For IR spectrum, make sure you explain how the dipole moment change is necessary, and you can also give an example. Okay. Next is again, okay, yeah. Next question. Draw a neat and labeled Jablonski diagram. Draw a neat and labeled Jablonski diagram indicating the excitation and relaxation processes. Draw a neat and labeled Jablonski diagram indicating the excitation and relaxation processes. In this year also, chemiluminescence again came as a question. So what is chemiluminescence, and explain with example. Chemiluminescence, explain with example. Next, right? The transmittance of a 0.01 m solution, the transmittance of a 0.01 m solution of a substance, the transmittance of a 0.01 m solution of a substance taken in a 0.1 centimeter cuvette, taken in a 0.1 centimeter cuvette is found to be 8.5%. Is found to be 8.5%. Determine the absorbance and the molar absorptivity. Determine the absorbance and molar absorptivity. Next, you write, what is meant by room temperature phosphorescence? What is meant by room temperature phosphorescence? Explain the importance. Okay. Now, what is this? Okay. Again, advantages of FTIR instrument, that one was repeated. So put another tick mark in front of that question. Then write, what do you understand by the fingerprint region of an IR spectra? What do you understand by the fingerprint region of an IR spectra? Explain the significance. What do you understand by the fingerprint region of an IR spectra? Explain its significance. Next question. Discuss clinical and biological applications of IR spectroscopy. Discuss clinical and biological applications of IR spectroscopy. Again, one question is repeated. Explain the factors on which fluorescence and phosphorescence depend. You've already noted down this question. Put a tick mark again. Explain the factors on which fluorescence and phosphorescence depend. Next, I'd already asked you to write down instrumentation of fluorescence and phosphorescence spectrometer. Here again it has come. Essential components of a fluorescence spectrometer. Explain with schematic diagram. So you'll be able to write instrumentation of fluorimetry and phosphorimetry. You will be able to write the diagram and the components. So put a tick mark wherever you have written. Put a tick mark again against the advantages of FTIR spectrometer. Again, in another paper it is there. What do you understand by the term fluorescence quenching? What do you understand by the term fluorescence quenching? Discuss the mechanism of fluorescence quenching. What do you understand by the term fluorescence quenching? Discuss the mechanisms of fluorescence quenching. This you can find in your study material. Okay, this you can find in your study material. Next again, right? Discuss the causes of deviation from Beer-Lambert's law. Here you have already, it has come in another paper earlier. Just put a tick mark against that. Discuss the causes of deviation from Beer-Lambert's law. Then write, describe the sampling procedure. Describe the sampling procedure for solid samples in IR spectrometry. Describe the sampling procedure for solid samples in IR spectrometry. Okay. Then again put a tick mark. This question also repeated. Various factors affecting fluorescence and phosphorescence. Various factors affecting fluorescence and phosphorescence. Next question. Explain the origin of phosphorescence and fluorescence. Explain the origin of phosphorescence and fluorescence with the help of Jablonski diagram. With the help of Jablonski diagram. What are the possible spin states in the molecule? What are the possible spin states in the molecule? Next, again, write a question. This is a numerical problem. A 5 millimolar solution of a nickel complex, a 5 millimolar solution of a nickel complex was taken in a 1 centimeter cuvette. A 5 millimolar solution of a nickel complex was taken in a 1 centimeter cuvette. The absorbance at lambda max is equal to 590 nanometers. The absorbance at lambda max is equal to 590 nanometers was found to be 0.45. Was found to be 0.45. Calculate the molar absorptivity of the solution. Calculate the molar absorptivity of the solution. Now what you will do here? You've been given the concentration, you have been given the path length, you've been given the absorbance, so the molar absorptivity you can find out easily. Okay, A is equal to epsilon Cl. Okay, A is equal to epsilon Cl. So you will apply the Beer-Lambert's law here and you can solve the numerical problem. Now another question, define bioluminescence. Define bioluminescence and how it can be used in the medical field. Define bioluminescence and how it can be used in the medical field. Again, one question was repeated. Factors affecting fluorescence. Just put a tick mark there. Both questions. Advantages of FTIR spectrometer and various factors affecting fluorescence. Put again a tick mark there. Then write, draw a generalized molecular orbital energy level diagram. Draw a generalized molecular orbital energy level diagram showing possible transitions in organic compounds. Draw a generalized molecular orbital energy level diagram showing possible transitions in organic compounds. Indicate various transitions observed for acetone in this diagram. Okay. So what will you do here? Which subject does it belong to? It belongs to UV. Okay, it belongs to UV visible spectrophotometry. So what kind of transitions will be there in the acetone? Whatever transitions will be involving the p, s and n electrons, those will be the electronic transitions. Okay, those will be the electronic transitions. Give one example. N to pi star. Okay, N to pi star transition of acetone can be given. Also, this can differ in various solvents. So you can also add how the acetone band of N to pi star transition, it can vary in different solvents. So this will be an added kind of notes which you can make how the acetone N to pi star transition can vary. Okay. So various electronic transitions you can write. Now write, interesting question, define molar absorbance and transmittance. Define molar absorbance and transmittance and explain the relationship between the two. Calculate the transmittance of a solution. Calculate the transmittance of the solution. Calculate the transmittance of a solution having A is equal to 0.2. Having A is equal to 0.2. Now we know that absorbance has a logarithmic relationship to transmittance. Okay, it has a logarithmic relationship to the transmittance. So if you have absorbance of 0, transmittance will be 100%. And if you have absorbance of 1, you will have 10% transmittance. So what is absorbance? Absorbance, apart from epsilon Cl, it also has another definition. Okay, that is log 10 of I0 by I. Okay, that is log 10 of I0 by I, and that is the reciprocal of your transmittance. So A is equal to minus log power 10 T. Okay, A is equal to minus log 10 T. Okay, that is the relationship between transmittance and absorbance. Another elaborate question has come. So you can write down the numerical thing also here. Again, you can write the numerical problem. A 6.5 into 10 to the power minus 5. A 6.5 into 10 to the power minus 5 molar solution. A 6.5 into 10 to the power minus 5 molar solution of copper complex. A 6.5 into 10 to the power minus 5 molar solution of copper complex taken in a 1 centimeter cuvette, shows the absorbance of 0.85, at lambda max is equal to 580 nanometers. At lambda max is equal to 580 nanometers. Another solution of unknown concentration measured at the same lambda max, shows the absorbance of 0.68. Another solution of unknown concentration measured at the same lambda max shows the absorbance of 0.68. Calculate the concentration of the unknown solution. So from the first part of the question, where we have the concentration, you have the absorbance, okay, and you have the path length. So from that you can calculate the molar absorptivity. Okay, you can calculate the molar absorptivity. Once you have the molar absorptivity, that will remain the same for the second problem. Okay, that will remain the same for the second problem. So in the second problem, you have a different absorbance, you have the same molar absorptivity, and you're supposed to find the concentration. So since the cuvette also that you are using is the same, so path length will remain the same, the absorbance is a value is given, and the molar absorptivity value is given. So you can easily calculate the concentration of the unknown solution and solve this problem. Okay. Next, again, this is a repeat but with a different twist. What is the visible range of the electromagnetic spectrum? Since the very first class, I had told you that you have to remember the ranges. Okay, the energy values, the wavelength, the frequency, everything you have to remember. And what kind of wave, what kind of spectra is found in which range of the electromagnetic spectrum. So this was discussed in the first class itself. So the question is that what is the visible range of the electromagnetic spectrum? What is the visible range of the electromagnetic spectrum? Draw a schematic diagram. Draw a schematic diagram for organic compounds. Draw a schematic diagram for organic compounds indicating all transitions in this region. Indicating all transitions in this region. Okay. Another, draw a neat Jablonski diagram indicating all processes involved. So this is a repeat question. Tick mark on Jablonski diagram wherever you have noted. Next, right? This has also been discussed in class. Illustrate the different types. Illustrate the different types. Illustrate the different types of normal modes of vibration. Illustrate the different types of normal modes of vibration of a carbon dioxide molecule. Illustrate the different types of normal modes of vibration of a carbon dioxide molecule. So we have discussed about different types of normal modes of vibration. To address this question, first you have to write down what are the total number of vibrational modes that are available for a molecule according to the formula of 3n minus 6. For linear molecules, it is 3n minus 5. And then you have to draw the structure of carbon dioxide. You have to show what kind of modes are possible, like symmetric stretching, anti-symmetric stretching, then bending, scissoring, all of that you have to show. And then you can also show that one of the modes, that is your symmetric stretching mode, is IR inactive because there is no change in the dipole moment, or the dipole moments cancel each other out. So this is how you will approach the question in a complete manner. So from the formula to the structure to the explanation, everything has to be on point. Next, right? Explain this mull technique. Explain the mull, M-U-L-L. Okay, explain the mull technique for handling a solid sample. Explain the mull technique for handling a solid sample in IR spectroscopy. In IR spectroscopy. Okay. Then next, again, question has been repeated for fingerprint region. What is fingerprint region? How is the IR spectra used to check authenticity of the compound? Okay. Another question from IR. List and briefly describe various sources of IR radiation. List and briefly describe various sources of IR radiation. If you remember, we had discussed various sources like a Nernst lamp, a glow bar, okay, incandescent labs. So all of that we have discussed. Define and describe various sources of IR radiation. Again, Jablonski diagram. Draw the Jablonski diagram. Explain various processes by which excited state of a molecule undergoes deactivation. Okay, so now there is this just twist in the language. So it is not just giving you a generalized Jablonski diagram. They are also asking you to show how deactivation can take place. Now, deactivation, when you're writing, be careful that you can show both radiation transition and radiation less transition. So in the Jablonski diagram that we had seen, both are there. Okay, both radiation less decay is there and with radiation decay is there. Whenever it is with radiation decay, it can be fluorescence or phosphorescence, and you can show these. Next is derive the Beer-Lambert's law, discuss importance in quantitative analysis using UV visible spectrometry. So this is very simple. Beer-Lambert's law, again it has come. Then Then very simple. Again, FTIR spectrometry has come, but here they have asked for the difference. How is normal FTIR different from IR and what is the advantages? So you can do it easily. Then this is a very specific question. You can use examples to illustrate this. How can IR spectroscopy be used to differentiate? How can IR spectroscopy be used to differentiate between aldehyde and ketone? How can IR spectroscopy be used to differentiate between aldehyde and ketone? Briefly describe the techniques used for recording IR spectra of solids. Briefly describe the techniques used for recording IR spectra of solids. Okay. Next you write, explain the type and role of monochromators. Now we have almost come to 2019 set. Explain the type and role of monochromators in UV visible spectrometry. Explain the type and role of monochromators in UV visible spectrometry. What type of sample holders are used for recording? What type of sample holders are used for recording UV visible spectra of liquid samples? What type of sample holders are used for recording UV visible spectra of liquid samples? Another question is repeated here. Draw the general molecular orbital diagram and show possible transitions for organic compounds using an example. So this has come in a previous question paper also. So if you have written down this question, put another tick mark here and read it carefully. Bioluminescence and chemiluminescence have again been asked, and they have been repeatedly being asked in question papers. Phenomenon of chemiluminescence and bioluminescence. Then draw a schematic layout of fluorimeter. Give light source used. So already I've asked you to pay attention to the instrumentation of fluorimetry and phosphorimetry. So this will be helpful. Draw a schematic layout of fluorimeter and give the light source used. In again the questions repeated. Explain the principle of FTIR. Give two of its advantages. So place a tick mark again. Next, illustrate different molecular vibrations for carbon dioxide molecule. This is also repeated. Another thing is coming. Differentiate between phosphorescence and fluorescence. Differentiate between fluorescence and phosphorescence with reference to its applications. In another paper I had seen with reference to the principle. In other question, it is reference to its application. So be careful when you are being asked to differentiate. Differentiate between fluorescence and phosphorescence with reference to its applications. Next, again the Jablonski diagram has been asked. Explain the phenomenon of phosphorescence and fluorescence with the help of Jablonski diagram. So only the language is being changed each time. Beer-Lambert's law has again come. Define Beer-Lambert's law, and another numerical has been given. This numerical we had solved in the very first class, so I'm not repeating here. This numerical had come, we had discussed already in the very first class. Then write, state any three sources of IR radiation. State any three sources of IR radiation. This is also a repeated question. Then again in 2020, this got repeated. Generalized molecular orbital diagram and the transitions for organic compounds. So this is an important question. Then again, carbon dioxide has again come as a question. Draw the vibrational modes of carbon dioxide molecule. Comment on their IR and Raman activities. Comment on their IR and Raman activities. Now, Raman spectroscopy, when we will see in the subsequent classes, we will discuss that. So just take it down as a question. Draw the vibrational modes of carbon dioxide molecule and comment on their IR and Raman activities. Another numerical of Beer-Lambert's law had also been discussed in the first class. So I dictated that question as well. Next, you write, state the selection rules. State the selection rules for vibrational spectroscopy. State the selection rules for vibrational spectroscopy. Bioluminescence, again it came, so place a tick mark there. And then in 2021, again questions are being repeated. Factors responsible for deviation from Beer-Lambert's law. Deviations from Beer-Lambert's law factors. Then you can take down another numerical. A solution containing 25 milligrams of K2Cr2O7. A solution containing 25 milligrams of K2Cr2O7 potassium dichromate per 100 ml. A solution containing 25 milligrams of K2Cr2O7 per 100 ml was taken in a 1 centimeter cuvette. A solution containing 25 milligram of K2Cr2O7 per 100 ml was taken in a 1 centimeter cuvette, and its transmittance was found to be 8. Okay, its transmittance was found to be 8 at 455 nanometers. And its transmittance was found to be 8 at 455 nanometers. Calculate the molar absorptivity. Calculate the molar absorptivity of K2Cr2O7. Calculate the molar absorptivity of K2Cr2O7. The molecular weight has been given as 294. The molecular weight has been given as 294. Now, the first thing that you will do for this question is take out the concentration. Okay, you will take out the concentration, and not just any concentration, you will have to take out the molar concentration. Okay, you will have to take out the molar concentration. So first, the molecular weight has been given 294. So what is the weight of K2Cr2O7 that has been given? That is 25 mg. Okay, so you will find out the number of moles of K2Cr2O7 that you are taking and that you are dissolving in 100 ml. So that is the concentration, 100 ml. But you have to convert that into molar. So you will take 1 liter, okay, or 1000 ml. So you have to find out how many moles of K2Cr2O7 you are taking in a liter, and that will be your molar concentration. So that is one quantity. The path length is there. Now the transmittance has been given as 8. From the transmittance, you find out the value of absorbance. Okay, we have already discussed the relationship between transmittance and absorbance. So if you have been given the value of transmittance, you find out the value of absorbance. So now what do you have? You have the molar concentration, you have the path length of the cuvette, and you also have the absorbance. So you can easily calculate the molar absorptivity. Okay, you can easily calculate the molar absorptivity. So this is how you will address the questions. Be very careful in these kind of questions which are for 5 marks. So you will have to clearly write all the formulas. You will have to write the steps. So stepwise you will have to write for getting the full marks. Next, again, the sampling methods of solids in IR spectrometry. This is also repeated. Sampling methods of solids in IR spectrometry. FTIR and normal IR, what is the difference? That is also coming. Various types of sources in IR spectrophotometry. This is also, we have covered this one. In 2022 also, the same kind of questions were being repeated, like generalized molecular orbital energy level diagram and the transitions in organic compound. Explain all transitions. Applications of fluorescence and phosphorescence. Okay, applications of fluorescence and phosphorescence. Now this is a little different question. Write down this question. Explain the stretching and bending modes. Explain the stretching and bending modes of vibrations. Explain the stretching and bending modes of vibrations for typical AB2 molecules. Explain the stretching and bending modes of vibrations for typical AB2 molecules. How would these differ? How would these differ in carbon dioxide and sulfur dioxide molecules? How would these differ in carbon dioxide and sulfur dioxide molecules? So first you will explain what is stretching and what is bending mode of vibrations. Then you will say for carbon dioxide it is a linear molecule, sulfur dioxide it is a bent molecule, although both of them are AB2 kind of molecules. Also you will say for non-linear molecules the total number of vibrations possible is 3n minus 6. For linear it is 3n minus 5. So you will first say what is the difference in the total number of vibrations. Then again you will say in carbon dioxide some of the vibrations are IR inactive because of symmetrical stretching. Okay, they are IR inactive. So you will draw the diagram and you will show all the kinds of stretching that are possible and all the kinds of bending and scissoring vibrations that are there in SO2 as well. So you will have to address the questions very systematically. Next again, applications of fluorescence and phosphorescence, that has also come. Then again, differentiate between phosphorescence and fluorescence. Differentiate between phosphorescence and fluorescence. Draw Jablonski diagram showing the two phenomena. So this is again a repeat question. Then again, instrumentation of UV visible spectrophotometer is coming. So you can write that. Draw a schematic diagram of double beam UV visible spectrophotometer. Draw a schematic diagram of double beam UV visible spectrophotometer and discuss the advantages over single beam spectrophotometer and discuss the advantages over single beam spectrophotometer. Now, for fluorescence, there are 2 points that we will be discussing. Please remind me. These two concepts are coming repeatedly in exams, but we have not discussed so far. So one is fluorescence quenching, different kinds of applications of fluorescence quenching, what types of substances are there in fluorescence quenching, that entire mechanism of fluorescence quenching is coming. So fluorescence quenching, just write down the concepts. We will discuss that. I will take it up in the concluding classes. Fluorescence quenching and quantum yield. Fluorescence quenching and quantum yield. And also the Stern-Volmer equation. And also the Stern-Volmer equation. STERN dash Volmer. VOLMER. Stern-Volmer equation. So these two I will discuss in the concluding classes. And you can also read from your study material. Also, another applications of fluorescence you must have learned, but this also you write. Discuss the application of fluorimetry. Discuss the application of fluorimetry for analysis of gaseous pollutants. Discuss the application of fluorimetry for analysis of gaseous pollutants. So please find out from your study material and from net also how the gaseous pollutants can be analyzed through fluorimetry. Also, particularly for sulfur dioxide, also one particular method is there in fluorimetry. So you also read about that. Okay, this applications of fluorimetry for analysis of gaseous pollutants and what it can be used for removal of SO2, how it can be used. So that is all for today. We have discussed the questions of IR, UV, and I did not find any questions from XPS in the previous year's questions. So you can just go like light reading you can do for XPS and UPS, but it is good to be prepared with everything. Okay. For IR and UV, mainly you have to concentrate on the different concepts. Numericals you have to practice for UV visible and be very careful with the units and the decimal places. Okay, and make sure you're doing everything in stepwise. For IR, remember all the absorption ranges. Okay, remember all the absorption ranges and the various vibrational and stretching modes and bending modes also you have to remember, and practice the diagrams for everything. Instrumentation is a must for all kinds of spectrometry. So बार बार वो आ रहा है हर kind of spectrophotometry में instrumentation is main. So you have to practice these very carefully. So that will be all for today. XPS को just lightly थोड़ा देख लेना. मैं भेज दूंगी. XPS का अभी मैं मेल कर दे रही हूँ. And बाकियों का मैं subsequently over the weekend I will be sending. And जो resources मैं दे रही हूँ अभी class में, please copy them and paste them in a Word folder or download them and keep in a folder. जब भी revision कर रहे हो, I would suggest कि देखो study material जो भी दिया गया है, that is your main thing. Okay, you have to go through your study material. There is no substitute. But since you're chemistry students and you will be doing more degrees in future or going for higher studies, तुम लोग को all these references, all the things will come in handy. Especially the long books. अभी के लिए नहीं चाहिए, but later also you will be reading again and again all these concepts. So that will be proving useful then. And as for the PDFs or the presentations, those are useful for quick revision. अगर याद करने की कोशिश कर रहे हो या visual तुमको अच्छा लगेगा, visually देख के अच्छा लगेगा, then you can find out from the PDFs and the presentations. But study material is a must. Study material के बिना उसको नहीं पढ़ के ये सब पढ़ने से नहीं होगा. So study material along with the questions, first you practice, then for revision you use these references. So thank you everyone. We are going to wrap up the session now. Okay, thank you so much. Good night.
Okay, thank you, ma'am.
Thank you, ma'am. Good night.
Thank you.